How are you guys doing? So today is like our last day of my last day of teaching. So these are the last set of topics here for the year that I wanted to get through. After today we'll have the last test and then some review for the AP exam. My plan for the test format is what? Well, let me tell you about the format. Maybe you'll change your mind about the optionality. Let you work with partner. Each partner can bring in their own separate sheet of notes, front and back. Okay. Does that feel a little better? Don't stop. What else? What more do you need here? Calculator throughout? Okay. Open book? Sure. Sure. So does that feel okay? Yeah, that sounds reasonable. All right. So this test has covered things from chapters 7 and 9. So we've looked at a couple of advanced integration techniques from chapter 7. We talked about integration by parts. We've talked about improper integrals, and today we're going to talk about trigonometric substitution. Those are the 3 chapter 7 topics. And then chapter 9 has been all on differential equations. We'll do a little bit of an idea from 9.1. We'll do a little bit from 9.4, and that'll finish us up in chapter 9. Does everybody feel okay with the plan here for today? How is your first week back from vacation looking testing wise? Would you rather kick this test into next week, or is next week look terrible also? I'm just trying to get a feel for when you'd like to do things. I have 2 tests. So you just want us to move on to doing AP review, and we'll take the test next week? Is that kind of the feeling everybody has? Okay. So I won't rush about figuring out the rest of the details as far as that format goes this week, since it's not going to happen until next week. But that's the loose format plan. Yes, Emma? Test 7. I think that we'd call this test 7, yes. Lucia? I think I'd let you guys pick them, I suppose. So I'll figure that detail out here by next class in terms of what we want to do there. I don't know how many. I have to count up how many people are in the class and make sure that there's an even number, and if there isn't an even number, what to do with the odd or whatever, Okie doke. All right. Here's my plan then. You guys all feel okay then, relatively speaking? All right. So what I want to do here on today is talking about I have one idea from 9.1 that I want to talk about, and that's it. And this idea from 9.1 is showing that something is a solution for a differential equation. Because we didn't do 9.1 in general, and this is one of those that can be a little tricky in terms of how to proceed, or there's usually an easy way through it, and I just want to make sure that we've done a couple examples of this process, okay? All right. So this example says, show that every member of the family of functions, yada, 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 is a solution of the differential equation, yada, yada, yada. So when it says here, show, what we're really talking about is like your work, right? So you can either start with y prime and go to y, or you can start with y and go to y prime, right? Each of these are reasonable approaches. You can go either direction. Which one of them is going to be the easier approach? Which process is easier, differentiation or integration? You should pick differentiation, right? The reason is that there are integrals that are not possible to do by hand. Is there any derivatives that are impossible to do by hand? None that we've seen. Okay? So you'd want to pick this route here. So how do I calculate y prime, or how do I do the derivative of this? What do I need to use? The quotient rule. Correct. So that's going to be the bottom times the derivative of the top. We're differentiating with respect to t. And then minus the top times the derivative of the bottom all over the bottom squared. Is everybody okay with how I've employed the quotient rule here? Okay. I'm now going to clean this up. So let's distribute things through. Is everybody okay with what I did there? What do you notice can happen in the numerator? Yeah, these guys can cancel out because they're opposite signs, and the other two are like terms, so we can add those two guys together. Is everybody okay there? Now, what's probably going to be easiest here, if I look at things, what's going on? So I'm here, right? What's the hang up though between the two? Is if I look at this expression for y prime, it's in terms of y, right? So what I think is probably going to be best here is to kind of meet in the middle. So I have an expression for y prime without y's in it. That's here. And I have an expression for y prime with y's in it. That's here. So I would either want to try to get my expression for this expression for y prime to have y's in it, or take that expression for y prime and try to get the y's out of it. Which one's going to be easier? Do we know what y is equal to? Yes, right? What's going to be easier, substituting the y into the in, or trying to generate that y somewhere in here? Substituting the y in, for sure, right? So that's what we're going to do here. Everybody feel okay? So I'm going to FOIL the numerator out. But I'm not going to FOIL the denominator out. The reason I'm not going to do that is because this 1 minus c e to the t squared is the same denominator I have in the other piece. And then I'm going to make a common denominator. Yeah, we'll show it in a separate step, I guess. Is everybody okay with what I did there? Okay. Now I got to make a common denominator with this minus 1. So again, that's going to be 1 minus c e to the t squared. And I'm going to FOIL it out in the numerator. So when I distribute that negative sign through, now that becomes plus, and that becomes minus. And I notice some good stuff happens. And I have 2ce to the t plus 2ce to the t. That's going to give me 4ce to the t, which is going to reduce with the 1/2 out front. And we're the same. Okay? For the most part, will they be this complicated? Probably not. This one was rough because the expression for y was pretty nasty. But this is the idea. To show that something is a solution to a differential equation, you can just differentiate the answer and show it's the same as the start. Is typically the easy route to go. You may have to make a substitution both ways and kind of meet in the middle. That's okay. Let's do another example here. This is one of the ones in the homework. Okay, where do we want to start? Let's start by taking the derivative of y Does everybody feel okay there? And then if we start with our other expression for y, or for y prime, and we drop in the equation for y, we have that. And then if I just move everything to the other side, if I take 2e to the x and subtract 4/3 e to the x, I get 2/3 e to the x. And then I subtract that guy over. And we're all set, right? Now they're exactly the same. What do you guys think? Is that okay? The place where this would show on an AP exam most likely is as a multiple choice question, where it would just ask, like, which of the following is a solution, to this differential equation, or here's a differential equation, which of the following is a solution to that differential equation. And this is the easiest way to check. Everybody all right? And I don't actually want you to do any of these. We'll just worry about some multiple choice questions from the MyAP on this. But I needed to show you this as an example. 9.4 looks at two particular special classes of differential equations. One where dy dx is equal to some constant times y. In this type of situation, the result is always going to be, or the solution to such a differential equation is always going to be an exponential. And even better, the constant out front of that exponential is always going to be like the initial value. So that's the takeaway. When you see a differential equation of this form, like dy dx is equal to 5x, where like y of 0 is 10, you can go straight to y equals 10 e to the 5x, and you're done. Like, you don't have to do a separation of variables. You can do that. You don't have to do like solve for the c. You can skip through all the algebra. You can look at that and go, oh, that's the form of a, oh, sorry, that should be 5y. That's the form of this type of differential equation. This is what the answer is going to be. That's the point of this. Again, the reason I'm showing this is because this can show up on the AP specifically as a multiple choice question where it's like, how the heck am I supposed to solve this convoluted differential equation inside of like just a couple of minutes? It's you recognize that, oh, this is just that exponential situation. I can go straight to the answer. Okay, so this is just like, want to recognize the form so I can shortcut through to the end. You guys see how I'm doing this, where I'm putting the numbers in the formula? But that's all we're doing, treating this as a formula, as a way to shortcut having to do like a separation of variables and like then solving for the constant and all that mumbo jumbo. It just can take a 5 or 10 minute problem and turn it into a 30-second problem. Now, the other situation here, this is a BC only idea. But I will make mention of this. So if we have a differential equation of this form, what you end up with is a logistic equation. So this is the shortcut here. So, for example, here we have this piece here. So this is what I need to see. So this tells me it's logistic. So my equation is the solution to my differential equation is going to look just like this. That's the form, yeah. So here we know that our K is 0.08 and our M is 1,000 and P naught, we're told, is 100, right? So my value for A is just going to be 1,000 minus 100 divided by 100, which is 9. So my equation should be 1,000 divided by 1 plus 9 e to the negative 0.08t. And I'm done. So again, I'm just filling into this formula. So the takeaway here is just to treat this type of differential equation as like a definition. And if I see that, I go, okay, I know exactly what this is going to look like. This is going to be a logistic growth. This is how I put the numbers into the right spots, and I'm done. Again, the idea is it's going to take something that's like a 10 or 15 minute problem to sort through, because this is not going to be a fun separation of variables, and turn it into like a 30-second, I know what the answer is going to look like. All I have to do is put the numbers in the right places kind of thing. Is that okay? This one I would like you to do just 1 through 11 odd to practice, making these substitutions. Is everybody okay there? Again, this shouldn't be complicated. I don't want to go through all the nitty-gritty details right now because it clouds the power of what we're saying. You just want to think about this as like, oh, it looks like this, then the answer has to look like this. I just have to put the numbers in the right spots, because that's really what we're saying here. We've done the nitty-gritty for you to realize that, like, oh, that's a pretty good deal if I can go straight to the answer and not have to solve a differential equation, because that can get pretty messy. It's okay? All right. Our last topic, and this is going to be the bulk of what our time today will be occupied doing, is using an integration technique called trigonometric substitution. So your indicator, your cue as to that you might need to do a trigonometric substitution, is your integral. It contains an expression of like an a squared minus u squared, an a squared plus a u squared, or a u squared minus an a squared, and there's no simple u substitution that would present itself. Okay, so if you have the integral of 1 minus, or the square integral of the square root 1 minus x squared dx, there's nothing you can do with that, with the rules that we have currently available to us. That is something that's tailor-made as a trigonometric substitution problem. Is everybody okay with that idea? So tool or the thing that we'll need to remember is we're going to be using these Pythagorean identities. Once we've made a substitution. So again, if you don't remember, like sine squared is 1 minus cosine squared, and cosine squared is 1 minus sine squared, and 1 plus tangent squared is secant squared, and 1 plus cotangent squared is cosecant squared. If you don't remember those, that's why I put them there, because it's been a minute, and probably the first two everybody probably remembers. The last two, it's probably 50-50 for most of us, right? Those other versions of the Pythagorean are often like, I can figure out which one is which, but like, sometimes it's just nice to have it written down for me. So what we're going to be able to do here is we're going to take advantage of those Pythagoreans to make some clever substitutions so that we can avoid having to, or basically allows us to cancel out the square roots. So for example, if I have like a squared minus x squared, if I pick x to be like a sine theta, and I drop that in, I'm going to have a squared minus a sine theta squared, right? And a sine theta squared is going to be a squared sine squared theta, right? That allows me to pull the a squared out front. I can write it like that. And 1 minus sine squared is cosine squared. And if I square root, that's going to give me the absolute value of a times, oops, that's not supposed to be an x, that's supposed to be theta. And I've gotten rid of the square root, right? So that's going to be kind of the goal while we're doing this, is that we want to make a substitution initially that recasts this problem as a trigonometric problem and gets rid of the square root. Now there's still some detail we have to resolve at the end that we haven't gotten to, but that's the general, that's the goal while we're doing this, is we want to make a substitution that cancels out the square root and recast this problem as a trigonometric problem. Peyton.
So you just randomly choose one, you just choose sines?
Well, it's not quite randomly. We'll talk about the criteria of how I knew which one to choose. But yes, you're getting right down to the crux of it. How do I know which one to choose? Yeah, you're dead on. That is the next appropriate question. So good on you. It's exactly what we should be asking. So here's the idea. So this is going to be kind of your guide for what substitutions to make. So if your expression is a squared minus x squared, we're going to pick x to be a sine theta. If it's a squared plus x squared, we're going to pick x to be a tan theta. If it's x squared minus a squared, we're going to pick x to be a secant theta. So that's kind of your guide here in terms of like, how do I choose which one to use? And now we're just going to have some examples here on to the finish, showing you what to do here and how to actually finish this guy out. Everybody good with the plan? Okay. So, which situation are we in? The first, second, or third? If I look up here. The first situation, very good. So we're going to say x is going to equal 3 sine theta Everybody's okay there? That's just me plugging the x's in. But what else do I have here? I still have a dx. How am I going to replace that and get it in terms of theta? Just like I did for a general U substitution, right? Is everybody okay with how I got everything now in terms of theta instead of x's? Now, at first glance, this looks much worse, right? Looks a lot more complicated, but it's going to get a lot better quite quickly. So if I look underneath the square root, I can factor off a 9 and I know 1 minus sine squared is cosine. So when I multiply these together, oops, we still have my integral symbol here. We're going to have 9 cosine squared theta. Well, the 9s are just going to cancel out, right? We'll just do integral. Is everybody okay there?
Isn't it 1 minus sine squared and cosine squared?
Yes, that's where, but the square root canceled the squareds, right?
Yeah.
So I took the square root of 9, that's the 3, and the square root of cosine squared, that's the cosine. But yes, you're right on.
Yeah.
That is 100% true. Still doing good? What's cosine squared over sine squared? Anybody recognize that? That is cotangent squared. Do we have an antiderivative formula for cotangent squared? We don't, do we? Right? But if I use the Pythagorean identity and rewrite that cotangent squared as cosecant squared minus 1, do we have an antiderivative formula for cosecant squared? Yes, you do, right? What is cosecant squared? The antiderivative of that is? Well, should be, there's a negative sign there that you're missing, but yes. So it should be negative cosecant squared. Its antiderivative is cotangent. So if we have positive cosecant, it's going to be negative cotangent. Is everybody okay to hear? Here's the hitch, though. Anybody see the problem with what we have? So the integration is done, right? But there's a problem. Who sees the problem? What was the original question? What variable is that in terms of? X. What variable is my answer in terms of? Theta. Does anybody see the problem now? Yeah, right? We have to somehow resolve this answer and get it back in terms of X. So not quite done. So here's how we're going to do that. This guy is going to be our key. If I divide both sides by 3, I have that sine theta is going to be x over 3, right? So if I draw myself a right triangle, theta is going to be there, and I have opposite over hypotenuse because I'm using sine. So to find this third side, I know that 3 squared is going to equal x squared plus y squared. Does everybody feel okay there? So now I have all the sides of this right triangle in terms of x. Everybody's good? So now, if I go back to the original, what is cotangent of theta according to this triangle? Cotangent is adjacent over opposite, correct? Everybody feel good there? What's theta going to be, though? Yeah, I can just take that expression for sine theta and use an inverse to get theta by itself. The triangle's not going to help me there. And that'll be our final answer on that one. Let's do another, yes? And I'll tell you guys right now, the part that most students get wrong is they don't do the back substitution. They're able to do the first part and get your integral answer in terms of theta, but they don't go then and take that answer in terms of theta and translate it back into an answer in terms of x. That's the piece that gets missed. All right, let's take a look at this guy. So if this one contains a x squared plus 4, what substitution should we be using here? This one, right? Now, does it matter that this says a squared plus x squared instead of x squared plus a squared? No, right? Because it's addition, it's commutative, it's fine. So we're going to say x is going to be 2 tangent theta. And then how am I going to substitute the dx? That's right. We take the derivative with respect to theta. What's the derivative of tangent? Secant squared. Is everybody okay? So if I factor out the 4 inside the square root, I have that, right? I'm just going to write it. Everybody's okay? And tangent squared plus 1 was secant squared. So when we square root that, we're going to have this stuff still on top. Going to have this. Oops. Is everybody good with everything that happened there? Let's do a little reducing. Everybody okay to hear? What are we going to do? Here's what I would do. Is there's no obvious u substitution here. So I would do this. Does that improve things?
Yeah.
Why?
That's percentage your identity or take the interval of that. Oh, you can do cosine divided by sine times 1 over sine. Those are both.
I mean, you can do that. It's not going to help you, though, because you're going to still be stuck in the same spot you were before. We're just going to turn into like cotangent time. What?
Substitution.
Yeah. What should my u be? Close. Oh, I guess u could just be sine. That might be fine too. So du would be just cosine theta d theta, right? All right, here we go. Everybody's okay with how I integrated 1 over u squared? Just thought about it as u to the negative 2. What's the problem though? What variable is this answer in terms of? What variable should my answer be in terms of? X. How many substitutions did I make? I made 2 separate substitutions, right? I went from x to theta and then from theta to u. So we're going to have to step back through 2 sets of substitutions to get back to an answer in terms of x. Is everybody ready for this ride? All right. What was the most recent substitution? This guy. So I know if u is just sine theta, we have this. Everybody's okay there? And then how did I get the thetas? I went with this. So here's theta. I have opposite over adjacent. There's that, right? And the expression that I need is for sine theta, which is opposite over hypotenuse. That's what's going to go now back into here. Oops. Opposite was x. Oops, still have my plus c. Oh, Mr. Kulik, you're done. You flip that. There we go. It's okay. All right, let's see. Do I have one more here set of example? Oh, I have two more. Well, I'll do one more anyway. Oh, this is the same thing, right? Oh, no, it is not. It's different. Okay. How about this one? What should we do? Yeah, this is a trig question, right? This does not need to be done using trigonometric substitution. Right? Do you see it? What should the u be? Yeah. Right, we can go and handle this without it. Okay, so just because you see the square root there doesn't mean we automatically need to do a trigonometric substitution, right? Take a minute, check to see if you can u sub it. If the degree of the x's underneath is like one more than the degree of the x's outside, probably have a good shot at being able to u sub that, right? Notice we had an x squared underneath the radical and an x outside of the radical. Good shot that that can be u subbed. And I would much rather do that than have to trigonometric substitute things, right? Because that's, while doable, it's a little bit of work, Mr. Kulik. All right. All right, let's do one more here. Since this is a real one that we have to actually u sub. Or actually have to do a trigonometric substitution. But this doesn't look like, like a x squared plus a squared or an a squared minus x squared or whatever. It doesn't look like one of those forms in the denominator. What am I supposed to do here? Not going to be helpful, but you're in the right ballpark. No, you can't square top and bottom of things. The answer here is completing the square. And that'll give us like an a squared plus or minus an x squared. So let's take a look at that. Okay, so if I look at 2x plus x squared, what do I need to complete the square there? A 1, right? X squared plus 2x plus 1 is a perfect square. Everybody agree? So we're going to add 1 and then subtract 1 right afterward, which is equivalent to doing nothing at all. Then I'm going to take this negative sign to distribute it to that negative 1 that we don't want in there. The negative of negative 1 is positive 1. So now we have the form of something squared minus something squared, right? Woof, Mr. Kulik. Are we going to have like a triple layer substitution here going on? I think that's probably what's going to happen here. So we have now that, we have our starting problem. That we can now rewrite as this. So make one u substitution. Oops. Come on. And then we have also that x is going to be u minus 1. Maybe I'll just, every time we make a substitution, we'll just change color. Everybody okay there? Now, since we are a squared minus u squared, what type of substitution do we need to make? We go back up and look. Oh, we are this one, right? So we need to be 2 sine u, or 2 sine theta, excuse me. So another substitution coming in. And if I look at that, that's 4 times 1 minus sine squared. And that's 4 cosine squared. And when we square root it, it's just going to be 2 cosine. Oh, and look at what's happening here, guys. Look, it's wonderful. Yes. That is some nice stuff happening. Okay, the integral of 2 sine theta is negative 2 cosine theta minus theta plus c. Okay. Now let's step back because we got to get this back to x's. So if I go to here, I know that sine theta is u over 2. So theta is opposite over hypotenuse. So cosine theta is 4 minus u squared over 2. So that's what I need. What is it? I have it. Oops. And again, we know here that theta is sine inverse u over 2. And if we go back to the blue now, we know u is equal to x plus 1. Oh, come on. Come on. So those guys cancel down. We have negative 4 minus x plus 1 squared minus sine inverse x plus 1 over 2 plus c. And we'll take that as our final answer. All right. That should do it for today here, folks. So your very last problem set is going to be, was 1 through 11 from 9.4, and then 1 through 11 odd on 9.4, and then 5 through 19 odd on 7.3. And that is it for homework and new stuff for the year. Pretty good deal, right? So the plan then for the rest of this week, we'll do some review stuff. We'll do a little bit of test review stuff, and we'll do some AP review on Wednesday and Friday. Tuesday next week, then we'll have the test 7, and then we'll continue with AP review after that till the end of the year. Everybody feel good? If you have a test and you're going to want to take want to opt for the retake option, we'll deal with that after test 7. So I'll start getting together a survey or a list of people that want to do a test retake. And we'll get that going. But we'll worry about that after test 7 is in the books. Does everybody feel okay there? Questions for me? Pretty good in terms of like what we have to do till the end of the semester. Yeah, like 2.5 weeks, right? 3 weeks, whatever. Okay. Everybody feel good?
Yeah.
As relatively good as you're going to feel? Was this hard today?
Yeah.
Trig substitution can be tricky until you get the handle of it. For sure. So like those 7 or 8 problems there, like really spend some time doing the 7 or 8 problems. Like don't just AI them, like settle in and like really try to sort your way through that. Once you got a handle on how to, the process, it's not so bad, but like 7 problems is going to be plenty of, can be plenty of time the first time through. Like that's going to be a good amount of time invested there. That should feel, they're not going to go quick, potentially. I mean, if you got it, they can be quick, but like your first time going through it can be rough.